Hello everyone. In this video, we will try to learn about the Kalman test for the observability. In the previous video, we already have established the concept of the controllability. We already have seen the different types, different criteria of the controllability. We have already developed the criteria for Gilbert test criteria for the observability and how the Gilbert test will work in order to determine, in order to find out, in order to confirm the observability of the system we already have done. So it is, if you have not visited, you have not revised that video, it is my again request to all the students, please go through that playlist. You can find out my playlist on the YouTube by writing the name Dr. Prakash Verma, Modern Control System, and you can just go through and revise this. So here we are going to discuss the Kalman test for observability today. Okay, so first the formal definition of the Kalman test we already have done same in the controllability. For the controllability, the matrix responsible, or you can say the input is responsible for in order to drive the state variable, and therefore the matrix B is responsible to determine the A, and both this matrix will determine the controllability, right? Controllability, right? Here in this case, the output matrix will drive the will drive the state matrix or the state variable, and therefore the CA both are the responsible in order to decide the system observable or not, right? So the formal definition, a linear system is said to be is linear time. Most appropriate word here is LTI, or can say the time linear time invariant system. Okay, or you can say so invariant system represented by the state model, by a state model, that is the state model is x dot is equals to x plus bu and y is equals to cx. Okay, y is equals to cx is completely said to be observable, is completely observable, it completely observable in case of when we have determined, we have built up that Kalman test for the controllability. At that time we have seen how this BAB, a square B, a to the power n minus 1 B, have decided the should have the full rank, right? We have built up that model matrix BAB, right? A square B up to the a power n minus 1 B, and this matrix is of full order, or you can say, or rank, you can say n, and then only the system was controllable, the same criteria. And here is completely observable when you can say, when completely observable if and only if and only if the matrix, which matrix, here BAB, and here in this case, in case of the observability, since C matrix, that output matrix is going to determine the state matrix, so you can say the model matrix, that is the observability matrix, C CA square up to the power CA to the power n minus 1 has full rank, rank and full rank n, and it will decide the you know the observability of the system. Okay, and also in other terms you can find out the mod or determinant of the key should not be equal to the 0, both are the same. Okay, if the determinant is 0, it means two or more than two column or row becomes same and the resultant is 0, and therefore this is the the rank will become lower than the full rank, and hence we are saying that the system is not observable, right? So what about the proof? Just now we are trying to find out the proof of this theorem. Why we are writing such type of equation in order to fulfill this criteria. Okay, so x dot is equals to ax plus bu. Ax dot is equals to, okay, wait a minute, sorry, x, okay, x dot is equals to ax plus bu, and y is equals to cx, and the state equation, the solution of this equation, the solution of this equation, solution of the state equation, the state equation is simple, very simple. X is equals to, xt is equals to, wait a minute, xt is equals to, you simply write e to the power at x0 plus 0 to t e to the power a t minus tau d tau bu tau d tau. We already discussed the homogeneous and non-homogeneous equation. Homogeneous and non-homogeneous equation, and in both this scenario we have find out the solution of this equation, and it is for the non-homogeneous equation, simple. Okay, so I am once again repeating my request. If you have not visited the previous video, please go through, try to understand, and then only you can easily understand these things in far better way. Okay, so what is the output matrix? The output matrix, the output equation is here, x, y is equals to cx, y is equals to cx. Since xt is equals to, simply the y is equals to, you can put here c into x. Okay, so c to the power at x naught plus c 0 to t c e to the power a t minus tau b u tau d tau. So this is the equation. Now one fundamental principle I am using here, okay, and this is very important. We are using two terms. First we will use ZSR. And what is ZSR? It is the zero state response, and second concept is the ZIR. So first I am writing this formal definition of the ZSR, and ZSR is nothing but the zero state response. State response is response of the system to input with initial condition, conditions set to 0, right? Set to 0. If your input, if your initial condition is 0, and then you find the response, then it means you are finding the ZSR, Z zero state response, right? And second case is the ZIR, that is the zero input response and zero input response. And this response, in this response you can say it is the response, to initial condition. Remember, initial condition, not here in this case initial condition 0, initial condition. We are going to find out the response to the initial condition with very important input set to 0. Input set to 0. We have put it here, input set to 0, right? And there is a ZIR. So we have the two ZSR and ZIR. So based on this above equation first, and you can say the equation A, okay, most appropriately I have written the name of this equation A. So since the matrix A, B, C, D and the input UT are known, okay, you can write here, since we have A matrix, we know B matrix, we know C matrix, we know D matrix, and the input matrix UT, okay, are known, are well known, right? These matrix are well known. So what we have to do, we have to zero state response ZSR can be Now what is the ZSR? ZSR is the, when ZSR means you are going to find out the initial the response when the initial condition 0. Initial condition 0. So ZSR can be determined. Just say ZSR can be determined, and you can say and can be subtracted also, and can be subtracted from ZIR. Okay, subtracted from YT to set, or to get zero input response. If you subtract this equation, then you will get the ZIR. So simple, in one word you can say simple, the ZIR is nothing but y naught is equals to c e to the power at x naught, and other terms, whatever the other term, what are the other terms? These are the other terms. Okay, or you can say simply the homogeneous equation we have considered, and for that purpose, and this value, you can say this equation, this line becomes simple, or this term becomes 0, and this term is negligible. Okay, so simply here we have written this term y naught is equals to c e to the power at x naught. Hence the state model x dot is equals to ax and y is equals to cx is to be considered for driving, the condition for observability is to be only considered. Okay, this is the state equation. This is, you can say this is the homogeneous equation. Yes or no? Homogeneous. Simply, yani it means simply we are considering the equation should be in the form of the homogeneous. And what is the meaning of homogeneous? The input is 0, right? So here we are considering this state for driving the equation, for driving the criteria observability, right? So as you know that e to the power at has the expansion like alpha naught t. We already have discussed these things also at the time of the Kalman test in the controllability. So if you're not able to understand how it is required, you can I'm referring you to go there, and you can understand from this. We have already proved this one. Okay, so alpha 1 t a plus alpha 2 t a square, and so on, alpha n minus 1 t a to the power n minus 1. We already discussed. Then your ZIR, zero input response is c e to the power a t x naught, right? Where input force is 0. Then we have calculated the zero input response. So you just write alpha naught t, alpha naught t. This just we have put in, right? E to the power 80 here, this expression just to put in here. Okay, so c into x naught, Similarly, you can write alpha 1 t plus c a, right? C a x. Sorry, my mistake is not plus. Okay, alpha 1 t c a x naught. Okay, then alpha 2 t c a square x naught plus alpha 3 t c a square, a q, okay, a q x naught, and so on up to the alpha n minus 1 t c a to the power n minus 1 x naught, right? Now try to write this equation into the vector form. Can we write this equation? Yes. How? Simply you can write here alpha naught t, alpha 1 t, alpha 2 t, and so on up to the alpha n minus 1 t, okay, into C CA square up to the CA to the power n minus 1, and last term is x naught. So this is the equation. Okay. Now you can conclude from this equation now, if the system should be the completely observable, or you can say the system is completely observable, then your output y naught t can be uniquely determined, right? Y naught t can be uniquely determined because we have to find each and every state. If each and every state, if you know from the output, then only you can say the system is completely observable. So you have to determine the each and every uniquely determined, you have to find out, right? And therefore the vector c ca squares up to the c power n minus 1 should be linearly independent, right? So I'm writing here, if the system is completely observable, then output y naught t can be uniquely determined, right? And therefore the vector, which vector? This vector. Okay, this vector, I am talking about this vector, right? This vector is c ca square up to the ca to the power n minus 1, right? Should be linearly, the value, each member of this matrix c ca square set power n minus 1 should be linearly, you can say linearly independent, right? So simple fundamental is, you can say, the observability matrix Q is c ca square up to the ca power n minus 1, has again the full order, or order rank sorry rank or rank n for the completely observable. Okay, so this matrix is known as, what is the name of this matrix? Simple, observable matrix or the model matrix, right? So the basic summary, you can say, I'm just writing the summary, concluding our what we have learned here up to this point. The system is said to be, the system represented by a state model, state model should be the linearly time variant LTI system. Okay, is said to be completely observable if and only if the observability matrix, observable or observability matrix has full rank. That's it. Okay, so I'm taking one example so that you can find out. It is very easy, however. Okay, so let's say one state model equation is represented here, -3 -1 2 0, and x plus 1 0 y u, and y is equals to given 1 minus 1 x. So you have to comment on the observability. Okay, comment on observability, right? So a is given -3, solution is simple, a is given -3 -1 2 0, and B matrix is given 1 0, and C matrix is given 1 minus 1 right? 1 minus 1. So simple CA matrix you can find 1 minus 1 into A matrix minus 3 minus 1 to 0, and obviously it will give minus 3 minus 2 minus 5 and minus 1 and minus 1. Okay, so your model matrix, or you can say the observability matrix Q becomes C into CA because of the second order system. So C becomes 1 minus 1, and it becomes minus 5 minus 1. And you can see here the rank of this matrix is 2, or it is better to find out the determinant of the matrix. If you find out the determinant of the matrix, then it will give 6 minus 6, and it is not equal to 0. And you can say that the rank of this matrix is 2, or the determinant is not equal to 0. The state model is completely controllable, is completely observable, right? Observable. So this is the fundamental. I hope you understand. Okay, so in the next video we will study, or we will discuss the factor cancellation test, and then one remaining test, that is the PBH, Popo Balovich Hottest test, we will discuss. Okay, so thank you.